Alright guys, you can keep talking. A tailback initially running at a velocity of 5 meters per second becomes very tired and slows down at a uniform rate of 0.25 meters per second squared. How fast will he be running after going an additional 10 meters? So, we need to write out our variables, VI, VF, A, delta X, and T. We have to figure out what we have and what we need. So if I were to draw a motion map for this, it says we're slowing down. So I can assume that I'm slowing down. I'm just going to assume that I'm slowing down to the right. Because I'm slowing to the right, my acceleration has to be to the left. It has to be negative. So even though it gives me this acceleration of 0.25 meters per second squared, I need to make that negative. My initial velocity is 5 meters per second. Delta X, 10 meters. Now meters is a unit for displacement, so this is going to be 10 meters. And it doesn't give us any time, and it asks us to find VF. So I'm going to use the equation that doesn't include time with it, but is VF squared equals VI squared plus 2A delta X. VF squared then is going to equal 5 squared plus 2 times negative 0.25 times 10. Okay, so that becomes, alright, when you solve this, you end up getting a VF squared equals 30. So when you take the square root of both sides, you get VF equals 5.5 meters per second. Whoa, that's wrong. That can't be right because we're slowing down. What'd I do? Okay, if you do the algebra correctly, you get VF equals 4.5 meters per second. Now I'm going to take this moment to explain. When I put this in my calculator, I didn't plug in this negative or take into consideration this negative here. And that's a big problem because I ended up getting the wrong answer. And, you know, you could probably follow my thinking. When I got a VF of 5.5, that didn't make sense to me because the problem told me that I was slowing down. If I'm starting at 5 and I end at 5.5, that's incorrect. That's impossible. I can't be slowing down and speeding up at the same time. So I knew that I needed to go back and check my work. So when this happens to you, go back and check your work because you'll get a 4.5 meters per second. Okay, number 5. Draw a motion map along the ramp for where it is released from rest. So because it's going down the ramp here, we're going to speed up. And then once it gets to the bottom of the ramp, there's no more acceleration, so it's just going to continue at a constant speed. So where we are speeding up, acceleration vectors have to go in the same direction. So this is my acceleration, these are my velocity vectors. Now let's look at number 6. Here we're starting on this side, so we are going to, it says V0 equals 0. That means we're starting from rest. So my arrows are going to get larger. And then here, there's no acceleration, so we're going to keep that same speed. And then as it goes up, we're going to start to slow down. There's my velocity vectors. Now, when we speed up, my acceleration vectors go in the same direction. When we slow down, my acceleration vectors go in the opposite direction. So my acceleration vectors are going to look like this. And there's no acceleration here on the flat portion. Alright, number 7. Focus on number 7 because you will have a question like this on your test. We need to look and basically decide if each of these, A is greater, less than, or equal to the scenario for B. So for part A, it says the displacement from 0 to 3 seconds. Remember, displacement is your change in position. We don't care how you got there, it's just your final minus initial. So if we look here at 3 seconds, they are at the same position. So even though B was speeding up, and A had a constant speed, they had the same displacement. So here A is going to equal B. The displacement from 0 to 1.5 seconds. Here is 1.5 seconds. So we can see that B's position is right here, and A's position at 1.5 seconds is greater than B's. Okay, if we were to put, just numbers here, maybe 1, 3, and 5 or something. We don't really know what those numbers are, but that doesn't matter. All we need to know is that A has a larger displacement. It's higher up on our position axis here. So here A is greater than B. Now if we look at the other side from 1.5 to 3 seconds, B, because he's accelerating, he has to go from a very small position to whatever this final position is. So he's actually traveling this displacement, and A is going from here to here. So if we compare those displacements, B is much greater than A. So I'm going to say A is less than B. Now for part D, average velocity from 0 to 3 seconds. Velocity is displacement over time. So if they have the same displacement and it's the same amount of time, they're going to have the same average velocities. And E is very similar. The average velocity from 0 to 1.5 seconds. Well, A has a greater displacement from 0 to 1.5, so A is going to have a greater average velocity. Here, A has a smaller displacement from 1.5 to 3 seconds than B, because remember, B is speeding up, so his velocity is getting faster and faster, so we have A is less than B here. Our instantaneous velocity at 3 seconds. So instantaneous velocity means we need to look at the slope of the tangent line at that point. I don't have my straight edge here, but that doesn't matter. If we look at B, at 3 seconds, B is much steeper, much more steep than A. So we have B is moving faster, so A's instantaneous velocity is less than B's. And the instantaneous velocity at 0 seconds. Well, it looks like B is not even moving to start out with, and then he speeds up. So B has a much lower velocity right at the beginning. So we would say A is greater than B. And then we have, okay, if the motion of B is uniformly accelerated, at what time will both graphs have the same slope? So, they have the same average velocity, so we have to figure out, well, what time is our average velocity equal to the instantaneous velocity? And if you remember, that happens at the half time. So here at 1.5 seconds, if I were to draw a tangent line at 1.5 seconds, then it would have the same slope as our average speed. So the middle time is where you're going to have the same velocities. 1.5 seconds. Alright, last one. You should be able to fully complete this based on your worksheet 2 in your unit, so I'm not going to go into too much detail here. But remember, you only have an acceleration if your position and time graph is curving at all. And the slope of your position and time graph tells you about the velocity, and the slope of your velocity and time graph tells you about your acceleration. So if I look at just these slopes, this is a negative slope, so I know I'm going to have a negative velocity. It's also, the slope isn't changing, it's not curved, it's a constant slope, so I have a negative constant velocity. Here, flat line, my slope is 0. That must mean I've stopped, so my velocity is 0. Now, if I look at just the slopes of these lines, here's a flat line, my slope is 0. Here's a flat line, my slope is 0. That means I am not accelerating at any point, so my acceleration is going to be 0. Now my velocity over here. If we look at this position and time graph, we start with a pretty steep slope, so that indicates that I'm going to start with a positive velocity because this is a positive slope. And then we are slowing down because my slope is getting less steep here. And ultimately, if I were to draw a tangent line at the top, that would be a flat line. So at this point, my instantaneous velocity is 0. And then finally, I start to speed back up to the left. I start getting steeper with a negative slope. So my graph is going to look something like this. Now, for my acceleration graph, I have to look at just this line here. So the slope of this line is negative, and again, it's not a curve, so we have negative acceleration everywhere. Alright, here we are speeding up and then moving at a constant speed. So because I speed up and it's positive, I'm not going to even use this negative region here. I'm going to start with a low velocity, and I have to leave 0. And then I need a constant velocity, so I get a flat line on my velocity graph. Now, here we have a positive acceleration because the slope at this section is positive. And then we have no acceleration, because when you're moving at a constant speed, you're not accelerating. I didn't draw these motion maps, but if I were going to, they would look like this. Here we're moving to the left at a constant speed, so I'm going to draw a couple arrows going to the left, and then we stop. There's just a couple dots there. Because it's a constant speed, there's no acceleration. Here for my velocity graph, I start moving pretty fast to the right, then I'm going to slow down and then speed up to the left. So my motion map is going to look like this. Change direction somewhere and start going to the right. Now here, whenever I am slowing down, my acceleration goes against me. So you can see I have a negative acceleration. And here when I start speeding up to the left, acceleration goes with my motion. So again, I have a negative acceleration everywhere, so everything matches up. For this last one, we are speeding up to the right, and then we're staying at a constant speed. So really I should have drawn more than one arrow here. Let's just say both of these are constant. Now while I'm speeding up, my acceleration vectors go in the same direction. And then here I have a constant speed, so no acceleration. Alright, make sure you study for your test tonight.